Welcome to Unit 6 of AP Physics 2, Geometric and Physical Optics. This is basically going to be about light waves and how they interact with things like mirrors and lenses. And so here are the equations in this unit, and we will cover them all in our content review. Let's get started. First thing to know, what is a wave? You might know waves from previous physics classes. A wave is just going to be a movement of energy. And so it comes in two different types, longitudinal and transverse. Longitudinal waves are when the motion is parallel to the movement of energy. And so it's more like pressure gradients. You have different parts of pressure, high pressure here, low pressure here, and it just kind of wiggles that way as it's moving in one direction. And transverse waves, on the other hand, is where the motion is perpendicular to the movement of energy. So the movement of energy is this way, but the particles or the molecules or whatever move up and down, which is perpendicular to the direction of motion. And so in this case, the energy is transmitted through areas of crests and troughs. And an example would be an electromagnetic wave. Longitudinal waves, an example is a sound wave. It seems transverse, like you've probably heard of it as, or seen images of sound waves looking like this, but it's actually a longitudinal wave. Now, what you can do with transverse waves is interesting. You can restrict it to a single plane of motion through what is called polarization, and we'll get to that in a bit. And so there are a few properties of waves that we need to know. Wavelength, amplitude, period, and frequency. Wavelength is just the distance between 2 points that repeat. And so this is one wavelength. Amplitude is just the distance between the midline or the resting position and a crest, which is also coincidentally the same thing as the distance between the resting position and the trough. The period is the time taken for one repetition, and the symbol for that is T. For amplitude, it's A, as you might imagine. And then frequency is the final one, and that's just the number of waves that pass through a point every second. And this one has a new unit, it's a hertz, and the relationship between this and period is that the frequency is equal to 1 over the period. And so hertz is just 1 over a second. So electromagnetic waves are transverse waves, but there's a difference between them and other mechanical waves. First of all, mechanical waves require a medium for contact because they use atoms to move. But electromagnetic waves do not require a medium. They just travel due to the electric and magnetic fields that exist in the vacuum of space. And so you have, while this is, for example, the electric field, there's going to be a perpendicular magnetic field that's also oscillating. And these two waves are perpendicular to each other. And finally, electromagnetic waves always travel at the speed of light because they literally are just light waves, whereas mechanical waves change their speed depending on the medium. Now, I mentioned polarization before. Polarization is when you use a device to restrict transverse waves to a single plane of motion. And you use a filter. And if you rotate that filter, you can rotate the plane of motion if it's an unpolarized wave, and an amplitude if it's already polarized. And so an example would be like this. You have a filter that this wave goes through, and then if it's already polarized, you can just change the amplitude of it, making it move at different amplitudes or just even flat. And you can also rotate the plane of motion if you rotate the filter as well. And so this isn't a big part of this unit, but you do need to cover it a bit. Okay, let's dive a bit deeper into electromagnetic waves. So like I said before, it's a set of two perpendicular oscillating electric and magnetic fields. And a change in the electric field causes a change in the magnetic field and vice versa. This is straight from our last unit, Unit 5, electromagnetism. We should know this stuff from that unit. And so you're just applying this to waves and something a bit completely different. Like you would not expect to see electromagnetism here, but it's going to be here a lot. And so, like I said before, you do not need a medium to propagate light, and it travels at the speed of light. And this speed of light, c, is equal to 3 times 10 to the power of 8 meters per second. And the equation for it is c is equal to 1 over square root of epsilon naught times mu naught. Does that look familiar? Epsilon naught is the electric permittivity in a vacuum. Mu naught is the magnetic permeability in a vacuum. And so when you multiply those two, square root it and 1 over, you get the speed of light. Another important relationship is that the wave speed is equal to the frequency times the wavelength. And so in this case, you can replace wave speed with c, the speed of light, because all electromagnetic waves travel at the speed of light. There's something called the electromagnetic spectrum, which is just the different types of electromagnetic waves. And so you're going to have long wavelength to short wavelength. And the entire spectrum goes like this: radio, then microwave, infrared, then visible. And within visible, you have red to violet. After that, you have ultraviolet, X-ray, and gamma ray. I'm not writing out the full thing because that'll take way too long, but always remember this: radio, microwave, infrared, visible, ultraviolet, X-ray, gamma ray. There's a few ways to remember this. My favorite is just the way to remember it is: raging Martians invade Venus using X-ray guns. It just uses the first letter of each of these types of waves to show them order from longest wavelength to shortest wavelength. Now, if you have electromagnetic waves in another medium, the frequency does not change, but the wavelength and the wave speed do change. So the frequency doesn't change because the frequency it corresponds to one of these different types of waves. And so that frequency doesn't change, but the wavelength and wave speed do change. Now, if you do change the wavelength without changing the frequency, that means wave speed automatically changes because they're related to each other. It's like changing the mass of an object without changing its acceleration, and that means the force applied must be different. And now, polarization of electromagnetic waves specifically, you can block certain wavelengths to change the color of the light. And the color of the light within this visible, it's from red to violet, and it goes like that. And so each frequency corresponds, or each wavelength as well, corresponds to a different type of color. And if you block certain wavelengths, you can change the color of this light. And you can even create 3D images by showing different images to each eye. That's how 3D glasses work. Okay, now, waves are what we call periodic. Well, most waves. The waves we'd be dealing with. Periodic waves just repeat portions of itself over and over again. And so this is a periodic wave. It just keeps on going like the same throughout. And a few examples of this. Electronic devices produce periodic oscillating magnetic fields. Magnetic fields in speakers, for example, move the diaphragm of the speaker, and then that produces the sound wave that you then hear. You can also change the frequency of this sound wave to change the pitch and volume, pitch and voltage to change the volume or intensity of the sound wave that you hear. And a simple periodic wave can be modeled using either sine or cosine. And so the general formula is x of t is equal to either a cosine of 2 pi ft or a sine of 2 pi ft, depending on which one you want to use. Cosine starts at the crest or trough, while sine starts at the resting position. So depending on which one you want to use, you use the certain equation. And this 2 pi f, where f is the frequency, t is just the variable time. And you can use this not only for electromagnetic waves, but for any wave that follows this simple periodic motion. Okay, that was a broad overview of basically waves. And now we're going to get into what you can do with waves and like refraction, reflection, and absorption and things like that. So reflection is when just light bounces off a surface, and the law of reflection states that the angle of the incident ray is the same as the angle of the reflected ray. And so usually you're going to have this diagram here where there's an incident ray, there's a reflected ray, and there's also this this transmitted ray. And so this is I, this is R, this is T. And usually this transmitted ray is going to be different. It's probably going to be something like that. It's going to be steeper usually. It actually depends. We'll get into that a bit later. But this angle here to the vertical is going to be the same as this angle here. That's what the law of reflection basically states. Refraction, on the other hand, is when the ray of light moves from one medium to another. So it's kind of like transmission, this ray over here, that's basically kind of like refraction. And the index refraction, n, of a surface is the ratio of the speed of electromagnetic waves in a vacuum to the speed of the electromagnetic wave in a specific medium. I remember saying that the speed of electromagnetic waves is always going to be the speed of light. That's in a vacuum. It changes slightly in other mediums. And that's why when you change the wave speed, you also change the wavelength, because the frequency always remains constant. And so this index of refraction n, the formula for it is just c over v, because c is the speed of light in a vacuum, which is just 3 times 10 to the power of 8. V is the wave speed of the electromagnetic wave in a specific medium. And this is also equal to the wavelength of that light in a vacuum versus wavelength of that light in this medium. They're just going to be the same. Since this speeds is just going to be f times the wavelength over f times the wavelength, and the frequencies are the same. So you can just cancel them out. And so another way you can write this is if you have two mediums, the index of refraction of the first one times the wavelength of the light in the first one is equal to the index of refraction of the second one times the wavelength of the light in the second one. Now, the index of refraction can never be less than 1 because you can never go faster than the speed of light. The speed of light is the fastest anything can go, and light is no exception. It cannot go faster than the speed of light c. And so your index of refraction can never be less than 1. If it's less than 1, that means that this is greater than that, which is impossible. If you have a larger angle when you're refracting, that means that that medium has a lower index of refraction. Good thing to note there. So I said usually it's going to be pretty steep, but if it's not steep, for example, here, this is a certain angle, this is another angle, where this bottom angle is larger than the initial angle, and that means that this surface it's going into has a lower index of refraction than the surface it's coming from. Another thing is Snell's law. Snell, S-N-E-L-L. It's basically a relationship between the indices of refraction and the angles. And we have a relationship with the wavelengths, but this basically says n1 times sine theta 1 is equal to n2 times sine theta 2, where the thetas are the two different angles, and the n's are the indices of refraction of those surfaces. When we're talking about refraction, we also have to talk about the critical angle, which is the angle of incidence for which the sine of the angle of the refraction is 1. That seems very complicated. But basically, this angle of refraction, the sine of that is 1. And so this means there's something called total internal reflection. And so there is actually no refraction through the medium. And this occurs at the critical angle. And so one way you can look at this is when you have this angle being such a value such that the sine of that angle is 1, that means it's basically perpendicular. It's basically going like this, which means there's nothing going through the surface. Sine of 90 degrees is 1, and so it has to be 90 for the sine of it to be 1. And so the angle of incidence is a certain angle that makes the angle of refraction 90 degrees. That means that there's no refracted light, and so there's total internal reflection. And this is only valid actually for light passing from a medium with a higher index of refraction to a medium with a lower index of refraction, because that means that this angle down here will be larger than the initial angle, the incident angle. And so that means you can have an acute incident angle while still having a perpendicular or a 90-degree right angle for the refraction angle. And so this critical angle theta c, or theta critical, is equal to the inverse sine of n2 over n1. And the way you can see that is because, well, if the definition of it is that the sine of the angle of refraction is 1, that means this is just 1. And so n1 times sine theta 1 is equal to n2. And so sine theta 1 is equal to n2 over n1. And just take the inverse sine of both sides. That was refraction. Now what about lenses and mirrors? This is probably going to be the hardest part of this entire unit. You're going to have different types of lenses and mirrors, and they're going to do different things. And so you have lenses. Let's start with lenses. You can use ray diagrams for lenses, and there's two different types, converging and diverging. Converging lenses are convex lenses that directs parallel light rays together. And so it looks something like this, kind of like an almond. If you have parallel light rays that are coming into this convex lens or a converging lens, it's going to direct it together to a single point. And so what can you do with this? It produces real images, and the focal point of this lens is in front of the lens. So it's going to be somewhere around here. In front of the lens. And so it'll be here because that's where the light rays converge. And the orientation of it is inverted. So if you have a function or a shape like this, you can use ray diagrams to show that this actually causes an inverted image. And so I won't get into the technicalities here because this is supposed to be a content review. So all I'm going to say is look into ray diagrams. They're going to make your life a lot easier on the AP exam. And you are probably going to have to do something like that with optics, especially with lenses and mirrors, because ray diagrams are really useful. I'm just going to say use ray diagrams, learn how to use them for different types of converging and diverging lenses and mirrors. Okay, so that's for converging. Remember, converging lenses are convex lenses that direct parallel light rays together. It produces real images, meaning that the image is real. It's not caused by a reflection of light or whatever. The focal point is in front of the lens and the orientation of the image is inverted. Diverging lenses, as you might imagine, is a concave lens that looks something like that. And it directs parallel light rays apart. And so it looks something like that. That is what it looks like. And so you might be wondering, then where's the focal point if the light rays are going apart and not together into a single point? Well, the focal point would be behind the lens, because even though these are going apart, you can draw these kind of ghost rays back all the way to a center point. And that's why this method produces virtual images, not real images, because you have to kind of draw back these light rays where they never intersected before. You're going to just draw back so they seem to intersect. So it's going to be virtual images. And the focal point, like I said, is behind the lens, and the orientation of this is actually upright. And so if you have a shape like this, you can use the ray diagrams to show that it'll be upright after behind the lens. Okay, moving on to mirrors. Again, you can use ray diagrams for mirrors. There's two types: converging and diverging. Converging is actually going to be concave this time. So it'll look like that. That is a converging mirror, but a concave lens would be a diverging lens. Be sure to make that distinction. So this also directs parallel light rays together. So if you have light rays coming in this way, they come back towards you and they converge. And so the focal point of this is going to be in front of the mirror, which is going to be kind of like this because they both are concave. It produces real images because the light rays actually intersect each other. It is real. And the orientation, once again, is inverted. Diverging mirrors are convex, so they look like that, just like a converging lens. And these direct parallel light rays apart. And so they're going to go like that. You're basically hitting it away from the original point. And so again, you have to draw back these rays, and you're going to get a focal point that is behind the mirror, same side as a converging lens, but it's going to be behind this time, because for a lens, in front of is where you are, in front of is where is kind of like behind a mirror. In front of a lens is behind a mirror. So always make those two distinctions. First, what's converging for lenses is not converging for mirrors, the concave convex differentiation. And also what's in front of a lens is not what's in front of a mirror. So make sure you understand the difference between those two. And so these produce virtual images, and the orientation is going to be upright. And there are a few equations that you can use for these. First of all, 1 over di plus 1 over do is equal to 1 over f. Di is the distance from the image, do is the distance from the object, and f is just going to be the focal length, the distance from the focal point to the object. And m is the magnification. So the absolute value of m is going to be equal to the absolute value of di over do, which is just the distance to the object and distance to the image. Okay, one table I like to talk about. You have focal length, you have do, and you have di on one side. And over here, you have positive and negative. So basically what this is saying is, if the focal length is positive, then this is going to be converging. If it's negative, then it's going to be diverging. If the object distance is positive, then it's a real object. If it's negative, it's a virtual object, which is very rare, actually. You're barely gonna have a virtual object. If the image distance is positive, it's going to be a real image. And if the image distance is negative, it's going to be a virtual image. And this is basically important when you're dealing with word problems about this. If you get something like the focal length is -2 when you use one of these equations, you're going to be like, oh, so it's going to be diverging because a negative focal length means diverging. Similarly, if you get an image distance that's 5 instead of -5, it's going to be a real image instead of a virtual image. So that's the hard part. Most of it is done. We're just going to get into one more thing interference and diffraction. Interference is when you combine waves. And so when you have two waves like this, the total displacement is going to be the sum of the two displacements. So at this point, they're the same. So it's just going to be twice as much. Here, these two add up to make that. And then here, these two add up to make that. And so you can just draw these points together, add them up, and you're going to get the interference or the total displacement. Constructive interference is when the resulting wave is larger than the individual wave. So they add up together. And destructive interference is when it's smaller. And so they kind of destroy each other. And if the distance between the two sources is exactly one wavelength, then it's going to be constructive interference, completely constructive. So it looks something like this. If that's one wave, and then this is the other wave, that looks something like this. This continues on as well. But if it looks like this, then it's going to be completely constructive, because at each point they add together to make it even bigger. So it's going to be something like that. On the other hand, if it's destructive, or if it's half a wavelength between each wave, it's going to be destructive interference. And so if it looks like that, as you can see, at each point, these both are opposites. And so it's going to just be flat over here. That's total destructive interference. And the reason why this is important is because you can use what's called diffraction grading. So you're using interference patterns to separate individual wavelengths. And so this is a very complicated topic that I cannot do justice to in this content review. So again, if you are confused by what I'm saying here, go back and review that. That and also lenses and mirrors, ray diagrams, things like that. And so you have this diffraction grading. It's the distance d between the two grates. And you have a wave that's being produced. And here you have the L, the distance from the grating to the wavelength, or to the wave, and a theta, the distance, the angle between the perpendicular line L and just the line that connects the diffraction grating to a certain crest of a certain wavelength. And that certain wavelength is numbered with numbers m equals 1, m equals 2, m equals 3, and so on. And y is going to be the wavelength of this wave. It's going to be the distance between two crests. And so the equation that describes this is d sine theta is equal to m lambda, where theta is the angle to a certain crest, and m is the number of that crest. Similarly, d is the diffraction grating, and lambda, or y, is going to be your wavelength. And then finally, we also have another equation, y is equal to m lambda L over d. In this case, y is going to be the wavelength of the produced wave. Lambda is going to be the wavelength of the wave you're sending in. And so that's also true of this one. Lambda is going to be the wave you're putting into the diffraction grating. Y is the wavelength of the wave you get out. And so if you have a higher wavelength wave, then it's going to be more spaced out and farther away than if you have a smaller wavelength wave. Final topic for this video, interference due to a thin film. If you have a thin film, then the light is reflected and refracted. And so if this light passes through a thin film, then constructive interference if the waves are in phase, and destructive interference if the waves are not in phase. Very rare you're going to get problems about this, but again, this is one of those topics I can't do much about because this should be just a quick content review. And so do look it up if you think you need to review that. And that's it for the content review. It's time to do a few practice problems about this. So we're going to start off with this MCQ practice problem. It says there's this light with a certain frequency that travels through air and enters glass perpendicular to its surface. And so it's going to enter like this. And that means if it's perpendicular to its surface, there's going to be no refraction. There's no reflection, and so no refraction. It's just going to go directly through it. And so the light ray doesn't really bend towards the normal. It cannot. It's already at normal. Normal just means perpendicular. So it's already perpendicular. And so C is wrong right off the bat. What about the rest of them, though? Technically speaking, we can also eliminate D because we know that the frequency does not change. It's only the wavelength of the speed that changes. So technically, we already know that our answers are going to be A and B. It says choose two answers. We already eliminated C and D. Let's just see why that's the case, though. Snell's law is one thing we can use, but that has to do with the angle. We don't want the angle. Instead, we use the other thing we know, which is N1 lambda 1 is equal to N2 lambda 2. In this case, N2 is larger than N1 because air is close to vacuum. the index of refraction of air is very close to 1 because it's very close to a vacuum. And we know glass is going to be greater because everything has a greater index of refraction than a vacuum. And so N2 is going to be greater than N1 no matter what. That means that to compensate for that, L2 has to be less than, or lambda 2 has to be less than lambda 1. And so the wavelength does decrease. That is true. And we also know that the wave speed is equal to the frequency times the wavelength. And as the wavelength decreases, then that means that the wave speed also decreases. And so B is also correct. Okay, moving on to the second problem. This is green monochromatic light. So green light, it's type of visible light. It has a wavelength of 550 nanometers. The NM is nanometers. And it passes through a diffraction grating of 2,000 lines per centimeter. Determine the distance between the first and second bright spots on a screen 1 meter from the grating. Okay, what equation do we know about this? Well, first we know that m lambda is equal to d sine theta. And so what we want is the angle, and then using the angle we can do some trig and find y. Or we can use the equation y is equal to m lambda L over d. So m, it says the first and second bright spots. And so m is going to be equal to 1. Lambda is going to be equal to, lambda is going to be the wavelength. And so that is going to be equal to the 550 nanometers. That's the wavelength of the incoming light. L is actually what we want to, is actually 1 meters. We want to find y, not L. L is going to be the distance between the grating and the screen. That's 1 meter. And D is the diffraction grating, which is 2,000 lines per centimeter. But technically, that's not going to be the exact value of D. We need to calculate D. D is going to be 1 over that because we want it in centimeters per line. And so it's going to be 1 over 2,000, which is equal to technically 5 times 10 to the power of negative 4 centimeters per line, but we want it in meters per lines. So that's going to be 5 times 10 to the power of negative 4 times another 10 to the power of negative 2, because we want to convert from centimeters to meters. So that's going to be 5 times 10 to the power of negative 6 meters per line. Okay, we already said that m is going to be equal to 1. We also want it for 2 and then just subtract them. And so it's just going to be equal to 1 times lambda, which we know is 550 nanometers, but we want to convert that to meters again. So a nanometer is going to be 10 to the power of negative 9. So 550 times 10 to the power of negative 9, and then times L, which is 1, over D, 5 times 10 to the power of negative 6. Plug it into your calculator, you're going to get 110 times 10 to the power of negative 3. And if you were just to simplify that into kind of more readable or more common terms, such as 0.11, that is y. The second one is when you plug in 2, that's actually just going to be twice as much as this. And so because this is 2 and nothing else changes, so that's going to be 0.22. And so now you subtract 0.11 from that, you're going to get 0.11. Now, this is not the exact answer because you can also do things with angles and get a more precise answer. But it's close enough to be 0.115. And so our answer is going to be 0.115. This is just, this actually is not an exact formula. I should have mentioned this earlier, but this is using the fact that at very small angles, sine theta is approximately equal to theta. And we're just using that fact here. At bigger angles, it's not always the case. So this is an approximation. If you want the actual one, you would just use this formula through and through. It's just we're using this formula because it's easier and it gives us an approximate answer. If it was an FRQ, we would use the first formula because if it's MC, we can just say, oh, this is close enough to that we can solve it. So yeah. And then finally, here's our FRQ question. This says that we have an experiment is set up with an object, a single converging lens, right? So this is converging lens. We know that means that it has to be concave because it's a converging lens, and a screen to make the image appear on the screen. The lens has a focal length of 3 centimeters. The arrangement is configured so that the image which appears on the screen is the same size as the object. The lens is placed at a position labeled 10 centimeters on the optic axis. So that's going to be right here. That's 10 centimeters. Draw a diagram of the experimental setup along the optic axis below. Justify your answer. Okay, that's part A. Shouldn't be too bad. We know that the lens has a focal length of 3 centimeters, and so it's going to be approximately 7 is what it is. Now, what we know also that the screen is back here somewhere, and that the object is going to be somewhere over here. We know that if it has to be the same exact size as the original object, it has to be exactly the distance, the focal length away from the focal point. So it's going to be at 4. If this is at 7, this is going to be at 4. Now, if you want an exact value of where the screen should be, it's going to be approximately 16. And so the way we know that these are the exact positions is because we know that 1 over f is equal to 1 over s or di plus 1 over do. And for di and do to be equal to each other, because this is the only way that the heights of the objects would be the same, you're going to have 2 over di is equal to 1 over f. And so f should be equal to 1/2 di. And so di is going to be equal to 2f. And so di or do, you can use the same thing because they're both the same. So do is going to be 2f, and it's going to be right here. That's going to be your justification for that. Okay, part B. If the converging lens were replaced with a convex mirror of the same focal length, explain how your experimental setup would have to change to produce an image of the same height as the object. And so a converging lens is it's similar to a convex mirror, but the mirror is gonna look something like this. Just that. There's no lens to it. And so what does this change about the setup? It's gonna say that the light will always stay on one side of the mirror, because in a lens it goes to the other side. It's not going to do that on a mirror. And so for it to have the same distance, it's going to be at the same position, and so the image will just be below the axis in this case. You're going to have to place the screen at the 4 centimeter mark in this case as well, because you want to capture it at the same exact position. Okay, and part C, in a clear, coherent paragraph-length response, explain what a virtual image is. Explain what steps would have to be taken to experimentally verify the existence of a virtual image. This is just one example. It's going to be a paragraph-written response, so I'm not going to actually write it down. I'm just going to say it out loud. So you can say something like, a virtual image is just a position where light rays appear to have converged, but no light is actually present at this position. They don't actually converge because this only occurs when the light rays are going apart. But if you draw back the lines, then you're going to get a point where it seems to have converged. And so you use what's called ray tracing that can yield a set of non-converging rays. And that converges the rays to a certain virtual image. And in order to experimentally verify that a virtual image exists, the image location can be used as the object location, and a second imaging system can produce a real image on a screen where the virtual image was its object. And so you're basically taking a virtual image and using that as an object for a second mirror or lens, or basically just a second imaging system is what it's called. A lens or mirror is just an imaging system. So you're using a second imaging system to take that virtual image and turn that into an object and create a real image using that. And then that gives you since there's going to be a real image at the end of that, you can say, oh, that means there must have been something to start with, which means that a virtual image must have been produced for there to be something to start with. So that wasn't very clear or coherent. If you were to write it down, write it much better than I said it. I just kind of made it up as I went along. But yeah, this is one of the common types of FRQ where you have to write a clear, coherent paragraph. And that's actually going to be it for our video today. This is actually going to be our penultimate video. Our last video will be Unit 7, which is about modern physics mostly.